Hi, I'm Vishesh, and I'm going to be talking about Physics 2 Lab 5. So, the overview for this lab. The purpose of this lab is to collect experimental data of a bar magnet falling through multiple conductive rings which make up a tube. We then created a computational model which replicates this interaction of the magnet and the conductive tube, and this allowed us to see the interactive forces at work as the magnet falls through the tube. And we then compared the data to the experimental data collected from the computational model's produced data. So, these are some important themes and equations we're going to be using throughout the lab. And the procedures. So first we used the phone magnetometer app to find and label the north pole of this bar magnet, and we dropped it down the aluminum foil roll and 5 times. And then we recorded the video of this magnet falling and used that to find the amount of time the magnet spent in the tube. And then we created a computational model of the magnet and aluminum roll interacting to find the expected produced data. Now, if we'd used a Ferris tube, this magnet would have just stuck to the sides of the tube and it wouldn't have fallen through, so this wouldn't work for the experiment we're trying to do. So here's some of the data we got from the experiment. On the left side, you can see the average time it took in the tube was 1.19 seconds. And an observation we had was that the magnet seemed to fall at a constant velocity once it entered the tube and not with just the normal downward acceleration of gravity as it did in free space. And that means that it fell slower in the tube than it did in free space. On the right side, we have some data about the aluminum tube and the magnet, and we took the magnetic moment from lab 3 and had that value. And we found the computational model calculated time to be 0.686 seconds for the amount of time it should spend in the tube. And this is different, probably because of lab 3 inaccuracies for calculating mu, and then probably another reason we'll talk about later. So here we have the coding sections we'll go through. So step 1 was just entering those values for the tube measurements. Step 2 is calculating and creating a magnetic field function due to this bar magnet dipole. In step 3, we calculate the change in flux function using flux equals the integral of B times dA, where we had that B function that we found earlier in step 2. Step 4 is going to be using the current equals change in flux over resistance equation, where we have change in flux from step 3 and resistance of the ring already. And so then step 5 and 6, we're going to be finding the force of the magnetic field of the magnet on the ring. And Newton's third law tells us that this is going to be the same as the force of the ring on the magnet. And then step 7, we're entering in gravitational force of the magnet, which is going to be negative mg in the y direction. And then we use Newton's second law to sum these forces. So in the magnet, there's that negative gravitational force and then the positive magnetic force of the rings on the magnet. And then in step 8, we're iterating functions of position and velocity, which update as the magnet falls through the tube. And this gives us instantaneous values we'll use for a graph. And that graph is on this next slide we see. So this model in general shows the relationship between induced magnetic field, change in flux, induced current, and magnetic force of a single slice on the tube. We then added up these magnetic forces on all the slices due to the bar magnet, and we get the magnetic force on the tube from the bar magnet, and this is going to be equal to the magnetic force of the tube on the bar magnet. And then once the magnet enters the tube, we can see on the right side of where we have the graph that it's no longer just having gravity acting in that negative y direction, so it levels off with a constant velocity. And then as it leaves the tube, we only have gravity again, so then it's going to fall again with acceleration. So the red rings in this diagram that we have are going to be representing the counterclockwise current caused by the increasing magnetic field from the falling bar magnet. And the blue rings above the magnet represent the clockwise current caused from the rings, which is caused from the induced current. And this is because of Lenz's law. So now we have the discussion. So what happens with the dynamics of the system when you flip the magnet around? Well, the initial B vector is going to be facing upwards instead. So now the negative dB dt vector is going to be facing down, which means that the current is going to be reversing directions. And ultimately, the red and blue rings that you saw previously are going to be switched. However, no change is going to happen in the magnet's falling velocity. How does the total time in tube of your real-world system compare to that of your computational system? Well, so the experimental value we had for time was 1.19 seconds. The computational model's time value was 0.686 seconds. So real-life factors probably also have like air resistance, and this extra force in that F net equation in the positive y direction would help account for why it took longer for the bar magnet to fall in real life than it did in the computational model. And then we had the question of what does the shape of the velocity versus time plot tell you about the forces? So like we said, before it enters the tube, there's only gravity acting downwards, so velocity is increasing negatively. When it enters the tube, gravity is balanced by the magnetic force, so the tube is going to have constant velocity in the bar magnet. And then after it leaves the tube, again, only gravity is acting downwards, so velocity continues to increase negatively. And then we had some last questions. What if the resistivity of the conductor were reduced as close as possible to 0? Well, since induced current is inversely proportional to resistivity, induced current would increase, which means the magnetic force of the magnet would also increase in the positive y direction, which means the magnet would fall slower ultimately. What if we had holes and slots cut in the tube, though? Well, holes are going to cause the resistance to increase, which means that induced current is going to decrease. So magnetic force on the magnet in the positive y direction would decrease ultimately, which means the magnet would fall faster, since gravity is going to be bigger in magnitude compared to just that positive magnetic force. Thank you.